Nobody's going fishing anywhere or anywhen.
Why would you go in the dark? I'm going fishing. That's just asking.
It's just a song.
I think it might be a euphemism, which is code, usually for something having to do with sex.
Really? Are you videotaping right now?
No, that's what a euphemism is. But I wonder, I mean, it's a, I don't know the song that well. I've heard it, but I don't know the song that well.
No, but are you like taping right now?
Yeah. I can say all manner of things like sex. I could say genitals.
No, I didn't.
Don't go too far.
Oh, if this is their first what the F moment, then I don't know. They haven't been paying attention. Good day, good times.
When you were hurting your wife saying that,
I skip those parts.
You skip those parts? Those are by far the most entertaining.
No.
Oh, okay.
They don't watch that.
That's too bad. They're missing out.
They don't generally watch the video.
They're too serious. Take themselves too seriously.
Yeah. Let it go nowhere, man.
Let's talk about problem set 8.2. So we had a couple of conceptual questions, and again, I stress there is a read chapter 21 sections 1 through 3, 5, 7, 9. Those are all good. They all lead up to this stuff. Do that. But let's look at these questions. Number 1, magnetic field lines, like electric field lines, never intersect. Suppose it were. Is that really the question?
Yeah.
No, we skipped that one. I was going to say that we didn't. That's a weird one. 2, number 2. That's a weird one. I didn't feel comfortable answering that myself, so I didn't want to assign it. Number 2, suppose you accidentally use your left hand instead of your right hand to determine the direction of the magnetic force on a positive charge moving in a magnetic field. Do you get the correct answer? If not, what direction do you get?
No, you get the opposite.
Well, why would we call it the right hand rule if you could use either hand, first of all? And yes, you get the opposite direction. So, if you did that, it would technically work for it using your left hand rule for a negative particle. I do that at Valley Fair, and then they always blank my picture. They think it's like a gang symbol or something. I don't know.
It does look like, feel like one. I don't know.
Yeah, that's right. Think of that while you're riding with the photos coming up, and everybody do this.
Everyone do it.
That's right.
Have you seen the picture of a guy doing a Jenga game? Roller coaster.
A what?
He's playing Jenga.
Oh, yeah, I did see that. Okay, so yes, in answer to the first question, it would go opposite. So, if you did the left-hand rule, it would work for a negative particle. But I strongly urge you not to do that. Always use a right-hand rule, and then if you're dealing with an electron or other negative particle, just make it opposite, because that'll be the negative sign. Number 3. A charged particle passing through a certain region of space has a velocity whose magnitude and direction remain constant. That's important. We had a special word or relationship if you have a charged particle, or any particle, moving with a constant speed in a constant direction. What can we say about that particle's motion then?
Constant velocity.
Constant velocity, which means what?
Not accelerating.
Not accelerating. You got it. And by Newton's second law, if we have no acceleration, what else can we say? No force. Or no net force. Because there could be forces, but they would all cancel each other out. So this is like our sum of forces, right? Okay, so this question asks, A, if it is known that the external magnetic field is 0 everywhere in this region, can you conclude that the external electric field is also 0? So we could have magnetic fields and electric fields acting on this, and so the sum of these forces, one would be the electric field force, one would be a magnetic field force. And we know that this adds up to mass times acceleration, but that's 0. Put it in terms that we've had from previous years. So we know that's true. I'm going to put that A down just a little bit because I want to expand this. How can we find the amount of electrical force on a charge in an electric field? That was from last chapter.
Minus like both sides.
But I'm saying, how can we rewrite and get a way to calculate this? Yeah, Justin.
Q V degrees times theta.
I'm going to put that over here
Oh.
under the magnetic part because we'll want that.
Q naught times E.
Close, not quite. QE.
What's QE now?
Charge. Q naught is just a way that they often denote a test charge that's in this field. So just, it's an electron or something that you dump in there. But these two charges are going to be the same. And when we add them, they must equal 0 because there's no net force. So A is asking, if we know that the magnetic field is 0, if we know this magnetic field is 0, which of course makes that whole term 0, what can we say about the electric field in this region? Must also be 0 because there's no other way around this. So yes, if the magnetic field is 0, then the electric field must also be 0. B asks, if the magnetic, or if the electric field, that should have been right. Woo. If the electric field is 0, must the magnetic field also be 0? Then the force would add up to 0. Is there any other way this could be 0? It's got a charge, so we can't say that Q is 0. It says it's going at a constant velocity, so we can't say V is 0. We could say B is 0. Is there any condition that this term could be 0?
They're opposite.
Not on the same graph.
90 degrees? What's the sign of 90?
One.
It's 1.
Sign of 180.
So if
With or against.
theta is 0 or 180 degrees, then this sign would be 0. The magnetic field might not be. There could be a magnetic field in this. It could be extremely strong, but as long as it's parallel to the motion, there's still no force because of this sign term. Because the magnetic field the force is always perpendicular to the magnetic field and the velocity.
What was the question again?
B asked, if the electric field is 0, does that also mean that the magnetic field is 0? And the answer is no. It might be 0, but it might not. If it's parallel to the motion, then it could be anything at all. Could be extremely high. So this is just getting into that right-hand rule thing that magnetic fields are strange. They don't act to push or pull things in the direction the field is going. It's always perpendicular to the field. Number 5. 3 particles move through constant magnetic field and follow the paths shown in the drawing, which I'll get up on the board in a moment. Determine whether each particle is positively charged, negatively charged, or neutral, and give a reason for each answer. So we've got a field, and everywhere the field, it's got these little X's. What do those little X's tell me about the field?
It's one in.
Going into the board. And we have 3 particles, A, B, and C. I think they're listed A, B, and C like that. It's 1, 2, and 3. Particle 1 curves up like that. Particle 2 is straight. Particle 3 curves like that. And it says, can you tell anything about these charges, if they're positive, negative, or neutral?
page 654 tells me to figure
Okay.
that out.
So how do you figure it out?
Well, I put the. What do you want me to tell? Oh, right, that one. I said that the first one is positive
How do you know it? Why do you think it's positive?
because it's going counterclockwise.
Okay.
Which way is the arrow?
So this one's going to the
Yeah,
left.
counterclockwise. And positive charge, right?
It is.
Okay, well that's what the.
I think it's a positive charge, I believe. Oh, it's saying determine whether each is positive
Oh, right, yeah.
or negative.
Because it's going counterclockwise, and the force is, the magnetic field is going the same way as that. I don't know how to explain it.
So you are trying to apply another one and sort of remember how this works. How can we figure it out, Chase?
Yeah, I had the opposite answer because I might have this wrong for reading the book.
I haven't answered this yet, so I haven't even considered
Because
really what it is.
Okay, if the pole is going into the boards, then the one going upwards is also kind of going inwards as well. I feel like.
These are all moving in the plane of the board, but the field is in.
So the one going upwards, when it's going inwards, is usually negative, and if I remember right from reading this book last night. So by that logic, I know 2 should be neutral, the other way should be neutral,
Okay.
and the other one should be positive.
Okay. Let's see if we can apply the knowledge we have to this.
So, could we use the right hand rule to figure it out?
Yes.
Because I was doing it on the bottom one just now, and if it is curving that way, the force has to be this way, but the acceleration is the opposite direction.
Okay. So that might tell us what.
It's
So
negative.
so let's apply the right hand rule. FBI, right? F is the easy one to remember. So FBI, I is the current. So this one comes in moving this direction. B is our pointer finger, and it's going into the board. And so our force, this is the best part about being a physics teacher, right here. Right here. The force would be up if this is a positive particle. This one does have a force in the upward direction. So that means it must be positive. This one, as I think maybe both of you said, this one doesn't have any force. What can we say about its charge?
Neutral.
Neutral. So 0 charge. That's not very clear. This one has a charge or a force in the opposite direction, so it still starts going that way. Magnetic field is into the board. We think the force then should be up or up and to the right or left, I mean. But it's not. It's the opposite direction. So it must be negative.
Yeah, you got the right answers, but I can't explain how. I know how I got that.
And if you can consistently get the right answer, I guess I'm fine with that. But
So it's
the right hand rule is the correct way to find it. Mm-hmm.
So it's just the thing you told us where it's
Now,
like you just flip it if it doesn't work.
Exactly right. Because the force, remember our force equation, Q, V, B sine theta, nothing else changed except for this sign. So if that sign is negative, the force is going to be negative, which means opposite direction. And number 7. Ooh, the drawing shows a top view of 4 interconnected chambers. A negative charge is fired into chamber 1. By turning on separate magnetic fields in each chamber, the charge can be made to exit from chamber 4, as shown. A. Describe how the magnetic field in each chamber should be directed. So our path is like this.
Beautiful.
Well, it isn't my first rodeo. And then we've got 4 chambers. Let's determine how the magnetic field, and this is negative, by the way. That's important.
it's electron.
Yep, it's an electron going through. So we have to determine what direction each of these is going to be. We have to use the magnetic field again, or the right-hand rule again. So FBI. We've got current going up. We know we have force opposite this, but it's a negative particle, so I'm going to still keep it like this. If this were a positive particle, the force would be to our left when my magnetic field is into the board. This is a negative particle and it's the opposite direction, so that still means into the board. Yep. Thank you.
Whose forces?
Can't even tell. This is really bold. Perfect. Now, force is up, but that's a negative particle. Motion is still that way. Force is up, opposite, because it's like this. So direction for this one must be out of the board at you guys. Remember that this is a negative particle. So we could do it alternatively, just so maybe it's easier to consider. The motion is that way. The force is up. So magnetic field would be in, but we know it's a negative particle, so the magnetic field would have to be the other direction too.
Okay.
That's right. You want to go?
Direction, force.
Sounds like you'd be threatening kids.
Not threatening them, I'm berating and embarrassing them.
Bad enough.
I have to build them I have to break them down before I can build them back up.
Good logic.
Motion is up. Force is to the left. Magnetic field is in, but this is a negative particle, so we have to flip that direction.
Out again, right?
Out again, just like this. And it's turning to the left or counterclockwise, so if you just continued that, it would continue to go in a circle, so that makes sense. Motion comes in, force goes up. So normally it looks like it'd come out towards you, but this is a negative particle, so it's back in.
In, out.
I'm still trying to figure out how to do that.
Come in.
Practice with these.
So,
FBI, right? Force, F. That's the easy finger to remember.
so that always goes at that 90 degrees.
And they're always 90 degrees. Now you can change this angle a bit if they're not, because velocity doesn't have to be perpendicular, to the magnetic field. That could happen all the time. But if it isn't, then that angle gets smaller, which means up here, the amount of force gets smaller. The direction is still perpendicular to these two, though, to the magnetic field and the
The
velocity.
force is where it's like it's being pulled to.
Right. Which direction is being pushed, and it's always perpendicular to the velocity and to the magnetic field. Yes, ma'am.
So we're just flipping whichever one we want.
One of
at
them.
the moment.
One of them has to be flipped. Any one will be flipped because that's the negative direction.
So it's like flipping. So is it flipping all of them or just
One of them. One. You asked if you flipped one, and I said yes. Stick with that answer. You flip one if it's negative. Any one, because it's QVB. That means this could be negative, or that, or that.
What are we flipping?
He's saying with a negative particle. We essentially flip any one of those with a negative particle. And then the second part of this, if the speed of the charge V when it enters chamber 1, if the speed of the charge is V when it enters chamber 1, what is the speed of the charge when it exits? Number 4
Would it be 1?
is V.
it's going the same direction?
It is, but does that mean that it's going the same speed? This is a speed question, not you can't see it when you're not looking at the book. It's not a vector question, it's a speed question. So it's not velocity. Certainly it's in the same direction in this case, but it doesn't necessarily mean that it's the same speed. It has undergone force, after all. Doesn't force mean that it's going to be accelerated?
Well, not
but it's got a force.
Oh, yeah.
F equals ma, right? Doesn't that mean?
What do you do when it's accelerated and curved?
What do you mean?
Acceleration can be curved as well, not speeding up or slowing down.
There are different ways we can have acceleration. Yes, it could be speeding up or slowing down. Magnetic fields don't do that. They don't push it in the same direction. If you enter this way and you want to speed up, you need a force that goes that way. But magnetic force never does it. Magnetic fields cannot accelerate things. Not in this manner. So the acceleration comes, as Matt said, in the change in direction, which still changes this, makes that a vector, changes that velocity. Okay, that's good. We had a few calculations. I don't want to go through each calculation, but I would like to take questions on them. Yes, ma'am.
So, when you went up to the F equals Q VB side, and you said we could flip the Q, the V, or the V, so does that mean we can't flip the F?
Well, if you flip one, then you have to flip the F as well. That's what that meant. So any one of them can be flipped. The direct, because the negative charge flips one thing. It flips the charge, but you could put that negative anywhere. Okay, we had a few questions. Do we have any, or a few problems to work out? Any questions on them? Okay, well, we can take those offline. I want to talk about one other thing